Yeah. Nice. Nice, nice. Nice. 403 to the HAZ, Mr. Nelson here. Hey, all right, we are doing, I got right here. Look at me go. We just learned what absolute value is, and that's basically two magical lines that says anything inside my magical lines must be positive. The absolute value of -2 is positive 2. Negative value of negative absolute value of 2. Well, the absolute value of 2 is positive 2, and then I'm taking the negative. So in this case, it's negative, because I'm only making what's inside the absolute value brackets positive. And then whatever I do to it outside, I do. So they're like a bracket. Sorry. I'm talking too much right now. Yeah, so that's that. So, just like every other thing we do in math, we can graph an absolute value function. So let's just start playing around with that, okay? So, Cartesian coordinates, x, und so y. Okay? Let's say I wanted to graph a linear equation. Let's just start really easy here. Y is equal to x. The most basic of linear equations. And if I were to make a table of values for this, and let's say I did, this is what, I'm just choosing random values for x, well not random, but, and then if y is equal to x, then at -2, I have -2 for y, right? I'm just using the function here to figure out what my corresponding y's are. And if I were to graph this, it would look like this, and it goes on forever in both directions, right? And at positive 1y, I get positive 1x. At x is equal to 2, I'm at y is equal to 2, okay? -1, I'm at -1, -2, -2, and it would go on like that forever. So then, what would the graph of the absolute value of x look like for the same domain of x, okay? So if I'm using the same domain to figure out, so the same inputs, these are my inputs, right? And this is going to spit out my y. So if y is equal to the absolute value of x, well, what's the absolute value of -2? It's positive 2. What's the absolute value of -1? Positive 1. 0, 1, 2. Oh. So this graph, the absolute value of x, it never goes into the -y territory, right? That's what makes it an absolute value. So what happens is it actually meets down here and does the same thing. So now, at x is equal to -1, we're at y is equal to positive 1. At x is equal to -2, we're at y is equal to positive 2. So the graph of y is equal to the absolute value of x gets rid of the negative component and just kind of bounces, right? So it's never going to get into the -y territory. So that's what a linear equation looks like, okay? And same thing with, I mean, we can do the absolute value of a lot of different types of equations. Let's say we wanted to work with a quadratic function now. Well, let's just work with our baseline and see what happens. Actually, we won't do our baseline, we'll do something very similar though. Let's say I had x squared minus 2. Okay, that's my function. And if I were to graph this, for some specific x's I'll use -5, -3, -1, 0, 1, 3, 5. I'm just choosing some x's as inputs, and I'm going to see what it spits out for y. And then these will be my coordinates that I can graph. So I'm going to graph it over here. Okay, so when x is equal to -5, well, what's -5 squared? 25 minus 2 is 23. What is negative 3 squared. It's 9 minus 2 is 7. What's negative 1 squared? Negative 1 squared is 1. Minus 2 is negative 1. 0 squared is 0 minus 2 is negative 2. 1 squared is 1 minus 2 is negative 1. And then everything else will mirror itself. And then if I were to graph this, it's going to hit a bottom at negative 2. At negative 1, it's going to be at negative 1. At negative 3, it's going to be at positive and negative 3, it's going to be at 7. Something like that. And then, I mean, it goes out to space at 5. It goes really high. So if I were to graph this, very crude. I'm embarrassed. Oh, that was massively terrible. So the graph would look something like this, okay? That's when I would graph it, and I know that my bottom occurs at x is 0, y is negative 2, and I cross the x-axis when y is equal to 0, which I'd have to plug that in to figure out the y-intercepts. Sorry, the x-intercepts. That's not why I'm here. So, this is what the original graph would look like, right? Now what if I had an absolute value function of that? So what if I said, okay, y is equal to the absolute value of x squared minus 2? Well, I start with this. I'm going to use the same. Man, why is red always letting me down like this? Okay, sorry. So x and y. I'm going to use the same x's. And y is equal to the absolute value of x squared minus 2. So it's basically equal to the absolute value of this. So it's 23. It's 7. What's the absolute value of negative 1? Positive 1. Now if I put negative 1 in here, negative 1 squared, 1, minus 2 is negative 1. What's the absolute value of negative 1? 1. 2, 1, 7, 23. So what happens now is basically the graphs are the same here and here because these were already positive. So the absolute value did nothing to this portion of the graph. It's the part that goes below 0 that the absolute value function really does its work on. And we can graph it. So now at 0, instead of negative 2, I'm at positive 2. And basically it's just going to mirror itself over there. So this is what the absolute value function would look like. Okay, and as you can see again, it's above 0. And that's how we work with absolute value functions. I just don't know that I want to teach much more on this. I mean, we can figure out what x-intercepts might be, y-intercepts. The x-intercepts on this graph and this graph, they're always going to be the same, right? It's still going to happen right here. The original function came down here like that and still crossed, but this guy, the x-intercepts don't change. So that's that. Yeah, honestly, I just think we need to know that the absolute value makes something positive. I don't think I want to do much more on this. I think that's enough to let you just kind of practice and struggle and do what you can. Yeah, cool. Have fun.